Another example about the uncertainties and the percentage uncertainty. The dimension of a box are recorded as follows. The length is measured with 5 with an uncertainty of 0.2. Then we measure the width with an uncertainty of 4. Sorry, 4 is a measured value, uncertainty is 0.1. And then we measure the height with an uncertainty. 8 is a height and with an uncertainty of 0.2. What is the maximum percentage error for the volume of the box? Okay, so we need the maximum percentage error, or you can also say the maximum uncertainty. Okay, so sometime what they normally use is they can use the value, like they can say, instead of saying the percentage uncertainty, they can also say maximum percentage error. So how we work out the volume? How we'll work out the volume? So the volume of this box, length, width, and height. So it will be length multiplied by its width multiplied by its height. We get its volume. So what is the volume? The length is 5, the width is 4, and the height is 8. So we multiply 5 multiplied by 4, 20, and 20 times 8 will make 160, and the unit will be centimeter cube. But what about the percentage uncertainty in V, the volume? Because the volume is calculated by length, width, and height multiplication. So when quantity, like a physical quantity, we calculate by multiplication, then what we do, we don't add the uncertainties, we'll add the percentage uncertainty. So what we have to do, the uncertainty in the volume will be equal to percentage uncertainty in length plus the percentage uncertainty in the width plus the percentage uncertainty in the height. Yeah, but the units are same, but the quantities are multiplied. When quantities are multiplied, because what will happen when centimeter multiplied by centimeter and centimeter, I will get another quantity which is centimeter cube. But when we were measuring, like example, length L was measured by using L1 plus L2. So centimeter plus centimeter was the final answer was in centimeter. So the units were not changing. That's why addition or subtraction, we just directly add the uncertainty. But multiplication or division, even though their units appear to be same, but we don't add the uncertainties directly. We always add the percentage uncertainty. So we'll work out the percentage uncertainty in length, which is uncertainty 0.2 divided by value recorded into 100. The uncertainty in the width, which is 0.1, the value recorded into 4 multiplied by 100. And the uncertainty in the height, which is 0.2 divided by value recorded into 100. So that will give us the percentage uncertainty in the volume. So which will be about, when we add them, it will be about 9%. Is it clear, this example? Anyone having a doubt or a question till this point? The main number, one of the student questions, should the main number have the same number of decimal places as the uncertainty? Yeah, it should be like this, but it can vary. Like sometime they can give you 2 decimal places, but usually it should be like this scientific representation. They should have the same number of the decimal places. Like example, when I say 2 or I say 2.0, 2 and 2.0 have the same meaning. So even this data I can write, like example, it's written 5 plus minus 0.2. I can write that as 5 plus minus 0.2 centimeter. That is fine. But because in physics, being a physics student, you use the number accurately. So that's why, because it can be measured to 1 decimal place accurately. That's why it was not written only 5, it was written 5.0 plus minus 0.2. So if it was not making any difference to the value, it's just a way to represent the data, the scientific way. And example 2.3, another example related to the uncertainty. So in this example, example 2.3, the mass of a block of a metal is 11.5 plus minus 0.5 kg, and its volume is 1000 plus minus 200 centimeter cube. How would you express the density of the metal? So how we represent the density of the metal? So first we find the density. Density is mass over volume. So mass divided by volume, that will give us the density. And see, if you see the number of the significant figure, here we have 3 significant figure, here we have 4 significant figures. So we represent our data in the least number of the significant figure of the given values. So density is mass over volume. The mass is given 11.5 and the volume is 1000 cm cube. So when we divide them, we got 1 because it's divided, so 1.15 into 10 to the power minus 2. So 1.15 into 10 to the power minus 2 kilogram per, this will be kilogram per centimeter cube because I did not change the unit. So I will keep that as kilogram per centimeter cube. Now, this is the density, but what we need the percentage uncertainty in the density. The percentage uncertainty in the density, how density is calculated by division of the mass and the volume. So the percentage uncertainty in the mass plus the percentage uncertainty in the volume. And here the volume, so what is the percentage uncertainty in the mass? 0.5 divided by value recorded into 100. What is the percentage uncertainty in the volume? That will be uncertainty in the volume, that is 20 divided by 1000 into 100. So that will give us the percentage uncertainty in the density. What's the answer for percentage uncertainty of the density? What's the answer for the percentage? (20) into 100 divided by 1000 and then plus 0.5 into 100 divided by 11.5. 6.34. Okay. Is it because someone sent 6.34, another one 4.35? Anyone else solve? I'm just asking the percentage uncertainty in the density. 6.34. Okay, so okay, total you mean? Okay, okay. So 6.34 is the total, right? So 6.34% is the total uncertainty in the density. Now we want, so what will be the 6.34%? 6.34% of our this result, which is 1.15 into 10 to the power minus 2. What's the answer? What's the answer here? (6.3% of 1.15 exponent minus 2. (7.29) 1 exponent minus 4. Okay. So I got 7.29 into 10 to the power minus 4. But now, okay, 7.29 exponent minus 4. Now we want to represent our data like the density is there. The density is 1.15 into 10 to the power minus 2. Plus minus the uncertainty is 7.29 into 10 to the power minus 4. So they don't appear in the same exponent, same scientific notation. That my density is in exponent minus 2. My density is in exponent minus 2 and the uncertainty is exponent minus 4. So that does not make sense, because you should use this when representing a data. I should use the same number of the significant figures. Now the density, because the density is what is important, so the density exponent will give the priority to the density exponent. Why? Because representing a density in 3 significant figure is more important than the uncertainty. So if I convert this into exponent 2, so 7.29, if I want to convert into exponent 2, that will be equivalent to what? If I want to convert the 7.29 into 10 to the power negative 4, I want to convert into 10 to the power minus 2. What will the answer? Yes. That's good, Ghulam, Ahmad. I want to convert only into 10 power negative 2. Like I just want to move the point. We have the point here, so I want to move the point 2 decimal places. So when I represent, so this will be equivalent to 0.072 into 10 to the power minus 2. Is it clear? Because like 7.29, it's 10 power minus 4 means it is divided by 10,000. So what I can do, I can represent my data as 1.15 plus minus 0.07, because this is 2 decimal places, so I will just use the 2 decimal places into 10 to the power minus 2. Is it clear, the representation of the uncertainty and the density? Anyone having a doubt or a question in this?
No, sir.
Any question or doubt?